I started recording. Okay, so I have defined what is called a real valued measurable function, but we need something more. We want some extended real valued function. So that's what I will define now. Okay, so if you have a function phi, if you have a measurable space, suppose if you have some x, this is x is a measurable space. Then phi from x. So I'm taking the closed interval. I'm taking including the minus infinity and infinity also. Okay. This is what is called an extended real valued function. It can take the value minus infinity and infinity. Extended real valued function, okay, is measurable. First, of course, phi restricted to the minus infinity, the real is measurable, which is the usual definition. And phi inverse of the singleton minus infinity and the phi inverse of the singleton infinity are measurable. Okay, that's all. There is one more additional condition that they are also measurable. Then we say it's an extended real valued function. So it's an exercise. It's the same thing. I mean, we just have one more condition. This is just the singleton has to be measurable. So you can, whatever we have till now verified, sum, product, and all those things. I mean, supremum, all the limit, all those things. You can check that. I mean, you only have to check for these two sets. This will also be measurable. Okay. I mean, your meeting will end in 10 minutes. There is some announcement. It says your meeting will end in 10 minutes. I don't know why. I'm in CMA account. Contact your IT team to upgrade to Zoom Pro for unlimited group meeting minutes.
Sir, today isn't the official class timing, right? So I think you don't have the access to use that CMI account.
That is true, but this is not an official class time, no? That is why. I don't know where. That's why.
Yeah, like in another course also it happened once. So this was the reason.
So it will end in 10 minutes or what?
Yeah, it will end and then you can just restart using the same link. We will join.
Okay, then I have to do the whole thing again and it will go for 45 minutes. Anyway.
Yeah.
Once it ends, I will tell you. Okay. So anyway, so you can verify that the supremum, lim sup, lim inf, all those things are measurable. So, okay, the exercise. Verify lim inf, lim sup of some phi n or I mean, they are all measurable. Okay. If phi n's are measurable, whatever we have done earlier, please verify those things. So let me not spend time on these things. So we have defined an extended real valued function. So then I want to prove the following proposition, which is very important. So our aim is to define integral. So integral for measurable function, positive measurable function first, and then we will do it for any real valued measurable function under some condition. So to do that, we want to approximate by, I mean, any integral is defined through limits. So we want to approximate by what is called the limit of simple function or step function. Whatever I defined as step function is also called a simple function. So that's what we will use. So, okay. So before that, I will make a notation. S plus of x equal to all those phi from x to minus infinity measurable simple functions. Okay. You know what is simple function? Our simple functions is also called step functions. Okay. I said step, I think, but simple function is equal to step function. Okay. Simple and step functions are same. Sometimes I call it simple function. Sometimes I say it's step function. Both are same. So then the propositions are following. Let's always assume that we have a measurable space and all those things. Suppose V is from minus infinity to infinity, measurable. Okay. Then there exists phi n, a sequence, and sorry, I want to take it from 0. Okay. So this is not from I want to take a positive function. Okay? So here also I want to say it's phi is greater than or equal to 0. So I mean, yeah, because I put plus here, it's positive, measurable, simple value, simple functions. Okay, this S plus is positive function. Then there exists phi n contained in S plus, such that phi n x increases to phi of x for all x in x. So any measurable function, any positive measurable function, any positive extended real valued measurable function can be approximated by simple functions. That's what this says. Okay, by simple function. Further, if phi is bounded, is less than infinity, then phi n x, above phi n x, phi n converges to phi uniform. Okay, I mean, this is increasing, phi n is increasing, and in phi n increases to phi of x. It's an increasing sequence of simple function, and the convergence is uniform when phi n is bound, when phi is bounded. Okay, so that's what. So given any positive, measurable, extended real valued function, we have to produce a simple function. So we will define the simple function and so verify that it is increasing, and then show that it converges pointwise. And in the case when it is bounded, you will show that the convergence is uniform. So that's what we are going to do. So for phi in phi measurable, define phi n by the following prescription. By what did I do? Phi n by the following. Phi nx equal to. So what we do is the following. We just take the interval. I mean, see, as I told you that this integral, this Lebesgue integral or whatever, is defined by partitioning the range. Okay, so we want to define simple function by partitioning the range. So what we do is the following. We define if phi x, sorry, not phi n x, phi x. If phi x is less than or equal to I, and greater than or equal to I minus 1, I by 2 power n, I minus 1. Okay. If then you define it by I minus 1. So we are partitioning the range by, I mean, for I equal to I less than or equal to n 2 power n, okay, greater than or equal to 1, of course, 1, 1. So we partition the interval 0 to n into 2 power n equal part 1 by, I mean, n 2, I mean, of length 1 by 2 power n. This interval has length 1 by 2 power n. So maybe I will write it again. I will write it in a nice form, the simple function equal to n if phi of x is greater than or equal to n. So here maybe to have it, this is just less than. I made that strict inequality. I have removed that. So it's clear how the phi n is defined. If the phi of x is between I minus 1 by 2 power n to I by 2 power n, then we define phi n x to be I minus 1 by 2 power n. Okay, this is between So you partition. So this is for I between 1 to n 2 power n. So we are partitioning the interval 0 to n. 0 to n into 2 power n, 1 by 2 power n. I mean, interval of length 1 by 2 power n into, I mean, the number of interval is n 2 power n. N times 2 power n. This is the number of intervals. Okay. And then when phi of x is greater than n, we are defining it to be n. So, or we can write it like this. Let us take En to be phi inverse of this interval I minus 1 by 2 power n, I by 2 power n, this interval. This is closed, this is open. Okay. For E n I. Okay. For I less than or equal to n 2 power n greater than or equal to. Okay. And f n I equal to phi inverse of n infinity. Then phi n x equal to summation I equal to 1 to n 2 power n I minus 1 by 2 power n. So this is the symbol we use for indicator function or characteristic function.